here. But so you can kind of see all the different parts, right? Exist what looks like new assignments, but they're not being counted towards your grade, right? Kind of the thing that's being counted towards your grade is kind of this midterm exam, right? That's what's kind of carrying that 30% weight. That'll get updated over spring break. Once I have that post-exam kind of questions in, I'll kind of add those points in so that'll get updated. So just give me a little bit of grace on that. We'll see. I'm going to try not to work too much over spring break. So I might not do that until the Monday after we get back, but I will get those scores updated to include that post-exam assessment as well, which needs to be completed by the end of the day tomorrow. Okay. Hopefully you've already done it. It's easy points. Just get on. Don't worry about it. Spring break after, hopefully you don't have any. Anyone have classes tomorrow? A couple people. Well, that sucks. But hopefully for most of you, right, you're kind of sorry not to add on. But so that's kind of where we're currently at. I also, problem set 3, you might see it graded over spring break. The TA's got the materials. I told them that, I understand they want them to take some time off as well. They said they might start on it kind of before spring break, try to get through it. But that may not appear until that week after spring break, that third problem set grade. Okay. Any other logistical questions for me before we kind of jump into material here today? Don't think I forgot to say anything. Yeah.
For the multiple choice section, is that, can we check that? For the multiple choice part of the exam, can we go in and check that right now?
It should be available to you. Let me know if it's not. So let me make sure I have it set so you can view it. It doesn't allow you, it's not allowing you to review it. Okay, I will make sure that let's try to make sure I do it right here. It should make those available to you after the due date is passed, which is the 11th. So why is it not allowing you to see that? Let's go see. You guys are getting a little bit of the back end here. I did a new quiz. It's supposed to say completing here. I know why. Because I converted it from old quizzes to new quizzes, and the new quizzes setting. I had it hidden until after the due date, which I forgot is an additional setting. So hopefully now you should be able to see it if you refresh and try to view that quiz. Can anybody verify that for me?
Yeah.
Okay, sorry about that. I forgot under the new quizzes that that's in a different location, so I have to go in before the due date and kind of switch that on and off. So, but yeah, the way I was coming up with those points was I simply took your multiple choice points and I was just adding those up there. So you should hopefully get the same value that you see for that midterm exam. If you just go in, add in your multiple choice points to the short answer points, and those pre-exam assessment points are already added in. Okay. All right. So where did we leave off? Right here. Okay. So we started talking about nonlinear relationships. And we're probably going to revisit this after spring break. I just don't think we'll get quite through everything today. And so I'll probably punt on a little bit of this, but I want to kind of touch on what we talked about last class before I move to the second part, because it'll give you a little bit, if you want to kind of start in the next problem set, I'll show you where that's at. I've got that posted. You can kind of start getting a pretty good amount of that done based off of even what we talked about this week. But we said that if I had a squared term in my regression, that marginal effect, right? When I'm thinking about finding the marginal, it's the change in something. So it's taking a derivative. So when I take a derivative of my regression equation, so derivative of y in respect to the thing that's changing, x1, the variable x1 here, I'm left with the coefficient on the linear term plus 2 times the coefficient on the squared term times the value of that x variable. So what's happening to that marginal effect? As x goes up, that marginal effect is changing. Now, whether or not it's going up or down depends on that sign, right? So I'll show you some visuals and then we'll kind of see how we maybe do this in Stata. So let's say I wanted to find the marginal effect and I had some population data here. An example we left off with was predicting COVID cases. So here, I think population, a 1 unit change represents 10,000 additional people. So just kind of scaling up that effect. So if I scaled this up, so I saw some people struggle with this one where I went from months to days. If I go from representing just one person to now a 1 unit change represents 10,000, what should happen to the size of my coefficient? It should go up, right? It's representing the change of not just one person, but 10,000, okay? So how would I find my marginal effect? So if I go back and I run this regression of the number of COVID cases, and I've got population, and remember here, it's just a different way of doing this in Stata. Instead of creating this new variable, which was population times population or population squared, I could use this kind of double hashtag and put a C dot in front of the variable, letting Stata know this is a continuous variable. I want to multiply it by itself and include that squared term in the regression as well. So if it helps to think about, if you created your own variable, this would be like whatever you called it, maybe population squared or a population SQ. So here's my coefficients, beta 1, beta 2. All I'm going to do to come up with a marginal effect, I now have beta 1 and beta 2. I can start to find the marginal effect of having an additional 10,000 people for cities of different sizes, okay? So, the population here is going to be my X1 variable. So for Bloomington, for example, I'm going to take the coefficient on the linear term plus 2 times the coefficient on the squared term times, well, if I had Bloomington, it's approximately 80,000 people, that would be a value of 8, right? Population here we said represented tens of thousands of people. So my marginal effect of having an additional 10,000 people in Bloomington, it would increase the number of expected COVID cases back when it was at its height of about 1,200. Right? So it's pretty substantial, right? But it's also 10,000 more people, right? Now, because that coefficient on the squared term is positive, what's going to be happening to my marginal effect of just having an additional 10,000 people, so the same 1 unit change, when I have cities of larger sizes? If that coefficient is positive here, as the population is larger, what's happening to my marginal effect? It's going to be larger. So if I think about maybe Indianapolis, and here I didn't even use like the surrounding metro, I just used the city limits of Indianapolis, so 2 million people. Well, there, an additional, I can kind of think about that would represent 200, right? If it's tens of thousands, I'm just scaling it. So my marginal effect is take the coefficient on the linear term plus 2 times the coefficient on the squared term times whatever population value I'm looking at, and I want to find the marginal effect up. So this is going to give me a marginal effect that's about 1,300. So notice that marginal effect is getting larger and larger as we're kind of having higher values of this X variable if both those coefficients are positive. So what I could think about doing is then graphing this out. And I'll show you how you do this in Stata, right, fairly quickly. So here was population. Here I'm just graphing out what the marginal effect of an additional 10,000 people or a 1 unit change was. That marginal effect is getting larger and larger. So, for New York City, we'd be somewhere over here, right? That marginal effect is going to be even larger. Okay. Is that any questions on that before we keep moving here? Yeah.
So for a negative marginal effect, if the sign for the coefficient for the square term would have to be changed, right?
Yeah, so let's say, so this is always going to be my marginal effect. Well, I forgot the 2. We can do it out of order, right? So I've got my marginal effect there, all right? Let's say this is positive, but this is negative, right? So we can put some values to it. Maybe this is 10, this is -5, right? Well, what's going to happen now if I want to plot out my marginal effect for different values of X? Let's say X could be like really low, right? Maybe initially, like let's say X was 1. What would my marginal effect actually be here? 1 times 2 times -5 is -10 plus 10. The marginal effect would actually be 0. For any X value less than 1, my marginal effect would be negative. For any, sorry, that's not true. I'm mixing up with the other example. Anything less than 1 here, right? What's going to happen? So let's just hypothetically say when x is 0, what does this become? So my marginal effect would be 10. As x goes up, what's happening to my marginal effect? I'm adding a larger and larger negative value. Eventually, it becomes 0. We said that occurs at the x value of 1. And then if I continue to increase x here, well, now my marginal effect is just decreasing. Yeah, so the sign of that coefficient on your squared term will change what this graph looks like, right? Will tell you whether or not, as x goes up, if the marginal effect is going up, like we had for the population example, or like in this example, if it was in fact negative, our marginal effect is decreasing as x gets larger. Yep. Any questions on this before we keep moving? So I'll jump the gun a little bit, but I know I have some stuff in Stata for this I think is interesting. What we would call this point here is going to be the turning point for our marginal effect. If we ever have the coefficients on the linear and squared term not be the same, right? So we'll kind of think about 4 different scenarios. We've already seen 2 of them. But if beta 1 and beta 2 are negative, that would mean that for different values of x, our marginal effect starts as negative and just becomes a larger negative value. So there is no point at which the marginal effect would be positive. Right? If I had a scenario where both of these, we already looked at one here with population, if they're both positive, it starts out as positive and just gets even larger. So anytime the coefficient on our linear and squared term are the same, we don't have a turning point. That marginal effect is either always negative or always positive. Now, we just worked through one where the linear term is positive, square term is negative. What ends up happening, we do have a turning point. For certain values of x, the marginal effect is positive. For certain values, it's negative, and there is a point where it's exactly equal to 0. We would have the same thing if I had the linear term being negative, but the squared term coefficient being positive. Well, that would tell us that initially, I didn't leave myself a lot of room here. I'll draw it over here so I have more room. Initially, if this starts out as negative, when the x value is 0, my intercept would have to be somewhere down here. However, because the squared term is positive, my marginal effect as x goes up would just be getting larger and larger. So here, whenever the coefficients aren't the same sign, this would be another example where I have a turning point, right? There's a point where that marginal effect is equal to 0. So how do you think I would solve for where that point is? If I've got an equation for the marginal effect, yeah, and this is what it's equal to, I would just set it equal to 0. And if a turning point does exist, right, I can solve for it, right? Just solve for x here. So this ends up being what? x2 is equal to beta 1 over 2 beta 2, negative beta 1 over 2 beta 2. So notice when these are of different signs, negative times a positive, I'll have a actual turning point. If these were both negative, negative times a negative times a negative, well, now the turning point is going to be, and I put x2 here, sorry, I'm writing and not paying attention what I'm doing. Well, then I would have a negative turning point. Well, for that variable, it's likely, for a lot of the variables we look at, we don't have negative values, right? It just wouldn't exist. Theoretically exists, right? But like I can't have negative populations, right? So a lot of the variables, it just won't make sense. The turning point would technically always exist. It's just that if we can never see x be anything lower than 0, we'll never see it in the actual data. Okay. But yeah, just to find that turning point, you just take that marginal effect equation essentially and set it equal to 0 and solve for that x variable. X variable. Okay. Any questions over anything here? Jump the gun a little bit on some of this, but I think based off the questions, this made sense. So I've got. Oh, did it not open it for me? I think I got handing back exams and I forgot to get this opened up. So we're going to keep using that same do file we were last class. Once I get Stata going. And I'm going to show you a way that you can actually graph out these marginal effects relatively easily. You don't have to worry about like plotting, getting the coefficients and plotting the points yourselves. There's a way to do it pretty quickly in Stata. So this might be part of what that fourth problem set asks you to do. So let's go to File, Open. We were on my OneDrive. This is the file that's up on Canvas, so nonlinear. You should only see the spring one. So we'll kind of come down here. I've got my global that I'll set. I think here we just did population. I'll kind of show you with the population data, and then we'll move to a different example. So there we go. Kind of got that population data set opened up. I'm going to scale it so it's in tens of thousands, run the regression, and then think about how do I get my marginal effects pretty quickly. Okay. So that's the same results we had in the slides. Okay. Now, here's where I can only do the following if I use this double hashtag method, right? If I instead run a regression where I'm using cases, population, and then I create the population squared variable myself. So I just want to show you just to kind of confirm you can do this and get the exact same results. Okay. Oh, what did I do? I spelled something wrong. There we go. So I'm going to run that regression and then run the following one. So notice, even if I create the variable myself, I'm getting the same exact coefficient estimates. The reason why I'm introducing this idea, and we'll kind of use it later on as well, of kind of not creating your own variable, but using this double hashtag is because if I want to use this built-in function, which is margins, to plot my marginal effects, it's only going to be able to do that for one variable name. So it can't use population and population squared. It can only use the variable, which was population, which you did include a squared term in that second regression. You just didn't create a new variable to create, to calculate that squared term. It was doing it for you. So if I try to run this regression, and then I then try to run this margins command, which I'll explain more in a second, it's actually just going to plot out. I don't even know if it'll do it for me. Let's see. It's taking some time. It'll do so, but it's going to do it. Oh, there we go. So what do I put? Margins plot. And I'll go back through this, like I said, more detail. I just want to kind of show you what it'll do if we don't do the right way. So notice here, I've got a straight line. So when I created that squared variable, it didn't factor that coefficient in at all. So it's only going to be graphing beta 1, essentially, the coefficient on the linear term. Well, we wanted to graph the marginal effect that was beta 1 plus 2 times beta 2 times the x variable. So the way we can do that is instead using this double hashtag method. Now, when we run this regression, we can then use this margins command. So what this will do is it says, okay, take the regression that was just run. Take a derivative of that function in respect to the variable you thought was not linear, population here. So it's going to take the derivative. Now notice what would be really useful. I can also do this not just for a squared term, but if I also included a cube term or a fourth power, right? It would still be able to take a derivative of that regression equation in respect to population. I'm only going to push you guys as far as doing a squared term in terms of calculating marginal effects, but you could go further. Now, it's not going to calculate it for every single possible population value. I'm going to tell it start out here. So this is kind of my starting value. So I put down here in the comments, notice it's take a derivative in respect to whatever x variable I'm interested, population. Then for that population variable, start out at 1, go up in increments of 1, all the way to the 1,000 value, right? So this is going to take a while because it's calculating the marginal effect at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 1,000, right? So I often put the quietly command in here because if I don't, it'll spit out at me all this output where it tells me the marginal effect at every possible value in this range, 1 to 1,000. That's a lot to look at. It slows my computer down. So a lot of times, if you throw in this quietly, it'll do the exact same thing. It just won't spit out at you all what those marginal effects are. So it's still running, it's still doing the same thing, but you just don't get all that output. Now, once I've got those margins calculated, or the marginal effect at every single value, I'm then going to go down here and use the margins plot command. So it's always going to be kind of the same syntax for us, just recast. We want to get kind of a nice line to show us the marginal effect. And then we don't want confidence intervals. I'll show you what happens if you take that off, but for anything I'm asking you to do, you don't need the confidence intervals. We just want to come up with that line that tells us the marginal effect. So if I run this, hopefully now, because I've used that kind of double hash, now I get my marginal effect, which we said the coefficient on the linear term was positive, on the squared term was positive. So the marginal effect should start out positive and just increase. Right? So that's a kind of a quick way of kind of graphing these marginal effects. Okay. Any questions on this before we keep moving here? So for the sake of this example, to go a little bit quicker, I'm going to change this to 10. That way it's not running through as many increments. Okay. So it's going, 1, 11, et cetera, et cetera. I also just wanted to show you, you can calculate these marginal effects even if you want to include additional control variables. So I forget everything that's in here, but let's say we want to do metro, let's do unemployment rate and vaccinated. So metro, unemployment rate, and vaccinated. So these are additional control variables we want to include. So if I run this regression, notice I can have this population variable be nonlinear while also controlling for other important omitted variables, right? Well, that's important because those coefficients would still have omitted variable bias. And in fact, part of the homework assignment, which we definitely won't get to this until after spring break, but I'll kind of revisit this and kind of show you how you would work through that problem. It could be that the omitted variable bias in my linear term coefficient is different than the one in my square term. Okay. So I've got some examples that we'll kind of walk through when we come back from break, but that could be the case. So I still want to be able to control for all these things I think are important. Right? Well, now even if I run this regression with these additional control variables, I can still run this margins command. And I'm going to run it quietly so it doesn't spit out at me all the output. Notice it ran a lot quicker, right? When I did increments of 10 instead of 1. I can then plot it. Now, it's not going to look a whole lot different, right? Because I can't see like the specific values, but if I looked at the actual regression output, I think before this was like 0.13 and this was 1300. So they're a little bit different, right? Because I've got added controls in now. But it can still, with these added controls, spit out at me or calculate these marginal effects for me, right? And kind of put them in this nice graph, okay? Any questions over anything here? We'll work through one more nonlinear example before we kind of transition to something a little bit different. Like I said, I don't know. Last half of the class, I go a little bit more slow. And so things won't be kind of week to week. Sometimes topics will bleed over kind of, multiple weeks here. So, I wanted to show you this as well. I mentioned to you. You can take off that no confidence interval, plot the same thing. It kind of gives you like what the confidence intervals would look like at each one of these different X values for your marginal effect. We're not going to dive into the reasons why they're like thinner at some points than others. I'm not going to ask you to do that, but it is kind of interesting to kind of see, well, here's the predicted marginal effect, but right, that's based off of a sample. We know that even for our marginal effect, just like for every coefficient, there will be a confidence interval associated with it, okay? But for us, like I said, we're just kind of worried about the marginal effect for the sake of this class. So the other data set I have up here on Canvas should be this small ft. Yeah, we're going to use that one, okay? So I've got some slides which we can revisit, but let's just open this up. I'm going to rename this variable. I'm going to generate this real quick. Well, I'll tell you what I'm doing here. So once again, I think I mentioned this last class, but right, March Madness is right around the corner, right? So I had this huge basketball data set, which was every free throw taken, and I forget the exact years, but it was over a certain number of years in the NCAA tournament. Right? In fact, I think this even went, it wasn't just the NCAA tournament, it was every basketball, any NCAA basketball Division I game. So I'm going to rename this variable to be free throw made. So this was just a 1-0 variable. So let's check it out. Here's my, oh, I just renamed it. Free throw made. It's a 1-0 of whether or not the free throw was made. Okay. So there's someone taking a shot, whether or not they made it or not. I'm then going to encode this position. Why might I want to encode this position? So we said that one thing we could do when I have categorical variables. So this position was like, were they a guard, forward, center, different positions on the team. If I want to control for what position they were, because I think that 7-footers tend to shoot free throws at different percentages than like smaller guards. If I want to include those dummy variables, but the original variable position looks like it's, oh, I can, there, nope, there we go. Okay, I can't use letters in my regression. So we said, what do we need to do? We're going to encode it so that it creates this new variable called position reg that I can use in my regression. Now, when I look at this new variable, it looks like it's still a letter, but notice it's changed it to blue. Every letter is represented by a number. So I can now use this to include different dummy variables, kind of using that I.dot command. So once again, this is where we're building on stuff we've already talked about. So I had this idea, I'm going to throw the kitchen sink at this regression that I have in mind. So there's all this like psychology literature. Have I went through this spiel with you guys about doing actions and you can do them more successful? I guess not, I'm getting blank looks. So with free throws, this applies to anything. There's all this physiology and psychology literature that when I do a movement, so they've done this with darts, they've done it with bowling. If I do a physical movement, let's see, I'm not a neuroscientist, but it's something about, it creates neuroplasticity in the channels in which I need to use to do that exact same movement, right? So when I do it successfully, my brain kind of builds these pathways for, remember, this is exactly what you need to do it successfully, right? So it's like a feedback loop or something. When it is successful, your brain kind of holds on, okay, what exactly did I do there? When you're not successful in a physical task, we don't see that. They don't see that in the brain. I don't look at brain scans, right? But this is the general idea. So they've done it with darts, they've done it with bowling, any physical movement. If you do it successfully, you're more likely on the next time you try to also do it successfully, right? Something about the pathways that are created in your brain. Like I said, I don't remember exactly all of it. I remember that neuroplasticity is the one word that they use because I, quite frankly, had never seen that before. So my thought process was, if I have all this free throw data, if I make a free throw, so usually they're kind of shot in sets of 2. So if I make the first one, holding constant my underlying ability, holding constant a bunch of other factors, am I more likely, given this literature and the neuroscience and physiology, I should be more likely to then make the second one, right? Holding constant all these other factors. So this is a somewhat powerful thought experiment. And what they did was they said, okay, look, I'm going to control for whether or not they were a starter. That should control for their underlying ability to some degree. Maybe there's stressful situations about the game. So maybe it's a game with larger attendance. So control for that. Whether or not they were at home or away, so they have to travel to this game. I controlled for the position that they played on the team, the year they were in school. So were they a freshman, sophomore, junior, senior? We then controlled for the divisions. So this was like division 1, 2, and 3. I then have this variable that I really want to know the impact of, which is, okay, there's some evidence that when we do a task successfully, we're more likely to be successful in the following time. However, what if it's a very stressful task, right? So this is the idea that maybe how stressful this task is going to impact how likely I am to kind of be successful on it in the future. Or sorry, how likely I am to be successful in it, right? So if I'm taking a free throw and the game is on the line, or I'm taking a free throw at the very beginning of the game when the score is 0-0, which one is going to cause me more psychological stress? The one where it's on the line, right? It's a tie game. If I make this free throw, we likely win. If not, it's very stressful. What do you think could happen to performance under stressful situations? Decreases. What happens when you take exams? I get it all the time. I knew it going in. I just got stressed out when yeah, the added stress, like I'm not going to ignore that, can reduce your performance. Same idea here. Even if we can control for all these other factors, this variable I call WPA, it is a measure that they use in basketball called the win probability added. So at the end of the game, if it's a tie game, there's 1 second left and you're taking a free throw, the win probability added is essentially 1. If you make it, you win. If you don't, you lose, right? This is the idea. At the beginning of the game, the win probability added is like 0. If you make it or miss it, there's still the rest of the game to be played. So it's somewhat of a measure of how stressful this shot should be, okay? So we might think initially, if the shot is somewhat stressful, it might have some impact on my performance. But as it becomes that WPA measure, as it becomes more and more of a stressful environment, what do you think happens to the reduction in performance? It gets even. So what did we just describe? A nonlinear effect. The marginal effect that would be nonlinear. So I use this neuroplasticity idea with the free throws. We'll revisit. I don't think we'll get that today, but we will kind of get back to that when we do interaction terms. So here, I'm going to run this regression where I said, okay, take this measure of how stressful this shot is, include its linear and its squared term. All right, that's that C dot double hashtag. So WPA, win probability added, we can all just, for the sake of this example, it's how stressful the shot was, okay? I'm controlling for all these other factors. So I'm going to go ahead and kind of run this regression. In fact, I don't even know why I put 2 in here. I'm going to control for the game seconds, how much time is left as well. So here, all these other factors constant, but the win probability added goes up by 1 unit for this free throw relative to another one. What's the impact on whether or not that shot is made? So I'm going to use that margins command. Now this win probability added, it's always between 0 and 1. And in fact, even towards the end of the game, the win probability is likely not 0 because crazy things could happen. So it's not going to be that high. So the kind of relevant ones, like if we were to summarize that WPA, it's like from 0 to 0.1 here. So it's relatively low, but it's a nice continuous measure of stress. So I'm going to measure the marginal effect from 0 to 0.2 in 0.01 increments. I'm then going to plot that, okay? So what it's going to look like here, I'm going to run this regression. Notice the coefficient on my linear term, if the shot is more stressful, it actually looks like I'm more likely to make the shot. Okay, well, we described when you're under stressful environments, you might be more likely to reduce your performance. But if you know a shot really matters, like at the end of the game relative to the beginning, what might you do a little bit more of? Focus, right? So maybe initially when it's a more stressful thing, so an example like a quiz, okay, I'm going to focus in to try to get these points. That should increase my performance, but it's not so stressful like an exam that it actually starts to decrease my performance. So what do we see? This measure of stress, the linear term has a positive coefficient, but the squared term has a negative coefficient. So that's going to tell us what? When WPA, this measure of stress, starts out at 0, the kind of increase in WPA will have a marginal effect that is positive. We're more likely to make the shot as initially it becomes a little bit more stressful. However, as it becomes more stressful, what's happening to the marginal effect? Well, if the coefficient on the square term is negative, that means my marginal effect is then going to be going down. So start out as positive. So a more stressful shot will actually improve performance. But as it becomes increasingly stressful, eventually we'll see the marginal effect becomes negative, or there will be a turning point, okay? So exactly where is that turning point? Well, we calculated all these marginal effects. We then plotted what that marginal effect is. Notice when the win probability added was from like what? 0 to about 0.04, right? So relatively low values. I think when I summarized it, the maximum was 0.1, right? So we're dealing with a pretty small range of values. But when it's relatively low stress, right? People are actually focusing more on that task. They're actually doing better, right? So this would be they're increasing the likelihood or their performance on these free throws, right? Our Y variable was dependent, or was it, sorry, our dependent variable was a dummy variable, just 1, 0. So our coefficients are interpreted as what? Changes in the probability. Yeah. Yeah, so you can think about it this way. If I'm going to evaluate the marginal product of labor, it's going to start out relatively high. What's going to happen as I hire more and more workers? It should be diminishing, right? So if I were to run a regression where I look at the number of workers and a number of additional, or the output that I'm getting from those workers, I would see something similar. Now, unlike that example, even my most inefficient workers, what's probably true about their marginal productivity of labor? It's probably still somewhat, it's lower, but it's probably still positive. Here we have a unique case where if the shot gets too stressful, after about 0.04, what starts to happen to the probability that they make the shot? Remember, it was that dummy variable as our dependent, so there was a change in the probability. Now my marginal effect actually becomes negative. I actually am less likely to make that shot once it gets over a stress level of 0.04. Once again, these win probability added are kind of hard to interpret, but we can just think about it as like increased stress of the shot. Okay. So I don't know, kind of a, I don't know, somewhat fun example where we can see like the marginal effect can be positive and negative for different values of this X variable. Okay. So I think I have all this here. So there we go. So like these are the results that we just looked at. I can kind of add in additional controls. I can look at the statistical significance of my nonlinear term, highly statistically significant. So just to kind of remember one thing we talked about last class, what is probably true about this regression? So even though I found statistical significance of that squared term, why might I be suspect of all of these results? How much of the variation am I explaining with my controls? 0.0089, so what? 0.8%? I likely have a lot of omitted variables here, right? Now, it's hard to kind of get these R squareds for some of these things to be high, but this one seems pretty low, right? So it might be good first evidence, but we might want to kind of continue to try to find more control variables. Now, this actually lines up with, I think it's the Yerkes-Dodson effect. This is a psychology effect where when a task becomes more stressful, initially, we often see the marginal effect as positive, but that as it becomes more and more stressful, that marginal effect usually hits a turning point and eventually becomes negative. Or the coefficient on the squared term is often negative. Right? So how can we kind of find that marginal effect? I kind of jumped the gun already earlier, and we said we could just take that coefficient, divide it by 2 times the coefficient on the squared term, and there's a negative sign out front. So I think I've got the values here. Did I? No. We could actually do that for our example. So where does this turning point exist? So let's look at, where was our results? There we go. So we had what? 0.54, so negative 0.5458814 divided by 2 times the coefficient on the squared term, which was 7.477836, right? This should give me my turning point. If I put this into a calculator or cheat real fast, put this into Excel, it should give me my turning point value, which visually we can kind of see. It looks like it's going to be right around 0.04. But using this equation, if Microsoft Excel ever wants to open up for me here, that was a CSV file. Maybe it was too large, I guess. There we go. Just gonna paste that into there. Sure enough, 0.0365 would be the exact turning point, right? So all I'm doing there is kind of using that marginal effect equation, plugging in the coefficient on the linear and squared term, I can get the exact value. Now, if I'm using Stata, I can kind of eyeball, it was somewhere in between 0.03 and 0.04, but I can get the exact value using that equation. Okay. Questions on this before we keep moving? Okay. So I'll show you another way that we could do this. So I can use the values. If I run this regression, and here's where it might be easier if you're wanting to calculate something like the turning point. Let me think if I can remember the syntax. I can't. So this is where it might be easier to do it this way. So let's say I did the same thing. But I'm going to include the linear term. And I'm going to create the square term. Okay? Now, the reason why I'm going to do this is because the syntax is a little bit easier if instead of calculating like this marginal effect or creating this marginal effect graph, let's say I just want to calculate the turning point. So we kind of already talked about this before, but so I'm going to create this variable, include that WPA and the squared variable that I created. So I should get the exact same results, right? It's just a different method. If I then want to calculate, oh gosh, I don't like typing on this. So if I wanted to calculate the turning point here, we said the general form of the equation is going to be I take beta 1 and divide that by 2 times beta 2. Well, once I run this regression, how can I actually call those values? Remember, if I use this underscore b, right, I can then actually use the coefficient that's associated with that WPA variable, right? Now, I'm then going to divide that by 2 times, well, what was beta 2? It was the coefficient, so underscore b, on that WPA squared variable. So this should calculate for me my turning point. What command did I need in front of it though? So if I ever just want it to kind of display a value to me, I can use that display command. So I think we did this in making predictions, right? We could use the display command and then take the coefficients, multiply them by this like hypothetical person. We can do the same thing here when calculating the turning point. Now, if I run this, sure enough, what value does it give me? That exact same value that we had found. Oh, did I forget a negative sign? I sure did. So here, -1 times, right? Now that should be better. There we go. I find that exact same value that we found in Excel, 0.036-ish. Okay. So we can use these stored coefficients and do it all in Stata, or we can take them, put them in Excel, do it by hand. When it comes to the problem sets, likely on something like this, if I ask you to calculate the turning point, you can do it in Stata using the display command like this, or you can do that portion of the problem by hand. Okay. I'm more focused there on, can you take that marginal effect equation, correctly identify what coefficient values you need, and then calculate that turning point. Okay. Any questions over anything here? Just making some sense, hopefully. Okay. All right. So covered all this. Let's think. We got 30 minutes left. I'll introduce these ideas to you, but we'll really kind of pick up with them on the next class. So let me think. Let me see if there's anything else in here that we could waste time with. So all this is natural log stuff. Yeah, I think that's the remainder. I wish we had a little more time, but that's okay. So we're going to go back here. We just left off. We can use this GPA original data, but I'll introduce the idea of a logarithmic function to you. So we had these squared terms. We can calculate the marginal effect that way. What could matter when we're looking at the relationship between two variables is not the unit changes, but sometimes the percentage change matters, right? So if something is going up by 1 unit, so for example, if a city has a population of 1,000 and their population goes up by 1,000, what impacts is that going to have on that city? Well, it just doubled in size, right? It's going to have some pretty big. What if New York City's population goes up by 1,000? What's going to happen? What are the infrastructure impacts on that city? Not much, right? That was very small. So sometimes it's not the unit change that matters as much, or we know that the same unit change, if it's a smaller percent, it's going to have a very different effect, right? Now, if that city of like New York doubles in size, right, and they get, I don't know how big New York, I forget the exact population, but if it doubled in population, well, that's going to have very large impact. So sometimes it's the percent changes that matter. So we're going to have this natural log function that we're going to use, and it's going to give us slightly different interpretations. Okay, so you guys have heard of this function before in some math class or something? No? Yes? Yes, I'm seeing some yeses. Okay, so if I run a regression, we're going to start to think about, in fact, just for the sake of time, we might even go through this more after spring break here. We're going to have 4 different types of regressions we can run. Okay, so I'm going to kind of give you a summary of them, and I think we'll dive in deeper into them after spring break. So this would be a really good summary to kind of have in front of you. So this one's easy, right? Because this is really all we've done up to this point. Linear. So the term here, the first word is your y or dependent variable. Second word is your x or your independent variable. How did we interpret beta 1 here? It was a 1 unit change in x predicts y changes by, I left myself not a lot of room, but beta 1 units. Okay, this is all the interpretations we've been doing up to this point. Okay, what if instead I think that it's not the unit change in x that matters, it's the percentage change in x that matters. So if I take the natural log of something, this is not quite technically correct, but for what we're going to do right now, it's okay. It essentially turns it from units into percentages. So now the interpretation you can think about is a 1 not unit change in x, but a 1 percentage change in x causes my predicted y value to change by. Now here's where it gets a little bit tricky, right? So it's not going to be, when we have these linear log models, it's not going to be that it changes by beta 1 units. It's actually going to be that it changes by beta 1 over 100 units. Okay, so the reason why is because if I'm going from like a percentage to units, you can think of this as like I'm going from percent to what would the units of a percent be? If we don't do percentages, it would be probability. So how do I go from a percentage to a probability? I would take that value and I would divide by 100. So we always start out, it's x that is changing. So linear model, 1 unit change in x, y would change by whatever the beta 1 is, units. We don't have to do any conversion there. If we take the natural log of x, it's a 1% change in x, but then to convert that beta 1 effect into the units of y, we have to divide by 100. Now I've got some math that supports this here we can kind of go through in a second, but for now, just kind of take me at my word with this kind of idea of moving between percentages and units. So what do you think is going to be true? Whoops. If instead, maybe I think that the units of x are what I should be using, but I'm more focused on percentage changes in y. So this would be a log linear model. So here it would still be a 1 unit change in x causes my predicted y to change by beta 1. But now what is the change in y? If I've taken the natural log, it's a change in the percentage. And if I'm going from units to a percent, what do I need to do? Multiply by 100. Okay. And then the only other one that we have would be a log-log model. this is where maybe I think the natural log. Hold on. I'm not going to just, I didn't leave myself a lot of room. So I'm just going to switch over here. There's no reason to kill myself because there's something else I want to show you here that's kind of relevant. So let's say I take the natural log of both. Well, now what's the interpretation of beta 1? A 1% change in x is going to cause my predicted y to change by beta 1. But if this is in percent and this is in percent, I don't need to multiply or divide by 100. Everything's in terms of percentages. Just like when I had linear models, I didn't have to scale beta 1 because everything was in units. It's only when they don't match do I have to worry about scaling that effect, right? Kind of going from percent to a unit or a unit to a percent. If they're both in terms of percentages, it's almost like the exact same thing we were doing before linear models. It's just now we have to say it's a 1% change in x will cause the predicted y to change by beta 1%. Does this at least template make some sense in terms of what we're doing with these different forward combinations?
So when you're taking the natural log, or converting it, not converting.
You can think of it as though you're converting that variable into percentages. Yep.
Can you just review why we have to divide by 100, multiply by 100?
So without going, well, I can give you here. This is the mathematical reason behind why, right? So the actual kind of, I'm taking natural logs of this, right? I can think about a change in x would be within my natural log. So the change that that's going to cause in terms of y, I'm going to have to kind of pull that out front. Well, I've got this, my change in y, or my actual y equation can be written out in this. I can rearrange it so that I've now got the natural log of x plus the change in x over x. This is going to end up being even a 1% increase. How would I interpret that? Well, that'd be 1.01 over 1. The natural log of kind of that 0.01 is essentially going to be kind of 1/100th of the effect. So that's why when I'm going from a log of x to linear, I'm going to have to take whatever effect I see and multiply it by 0.01. Sorry, not multiply by 0.01. Well, yeah, multiply by 0.01 or divide it by 100. Okay? So I'm not going to expect you to know all of this math, right? I'm telling you, there is justification for why that interpretation is the way it is. If you want to talk more about it, like during office hours, we definitely can. For what I'm going to expect you guys to know, I would just memorize what we just covered here. That if I've got a linear log model, that change in x is a percentage change, and the predicted change in y will be beta 1 divided by 100. And to make that make sense, I would think about it as, well, if I'm going from a percentage change to a change in units, it's like percentages to probabilities. How would I convert a percentage to a probability? I would divide by 100. That's probably an easier way for you guys to think about it. And all I'll expect you to, like, I'll make, ask you for an interpretation and want you to be able to do it that way. I'm not going to ask you to kind of give me any mathematical support as to why that is the correct interpretation. But here's why. So if I took my original equation and I thought about what change in x is going to have on the change in y, but that change in x is occurring within my natural log function. I know the original y equation was up here, so I plug that in. I rearrange some things. I'm left with this. The natural log of 1.01 over 1 would be 0.01. So it's going to be my coefficient times 0.01, or my coefficient divided by 100 is another way of saying that. Yep. Is that kind of what you were getting at? I know that's not like answer. Well, it's kind of answering your question, but I'm not going to focus that you can kind of do every line of this proof here. Yep. Any other questions on that before we keep moving? Okay. I don't think there's anything else I want to say here. I think I'll save this. I might jump the gun a little bit here. We won't look at examples. I've got some of it in this slide, but we'll just talk through it. So I'll probably start here. So if I'm using these, sorry, if I'm using y, hold on. Oh, I know why. There we go. So I'm not thinking about what I'm doing. There we go. So if I'm using these different log, linear log, linear models, I can now make these interpretations, right? We'll work through more examples after spring break. What types of variables can I not use these logarithmic regressions for? So this probably goes back to your math background. What's the natural log of 0? So if I look at that graph and you look at it, it's actually like it approaches this. The natural log of 0 is actually undefined, right? So it doesn't exist. So I can't take the natural log of 0. So what types of variables can I not use? For sure. Dummy variables for sure, right? Especially if I have a dummy variable as my y variable, I definitely can't use a logarithmic specification, right? So what am I forced to use? Well, let's say my y variable was a dummy variable. Can I use a log model? Can I use a log linear? Can I use a linear log? Yes, right? Because my y variable was the one that was 1, 0. I'm not taking the natural log of that. So yes, I could use a linear log, but I can't use these two. So I could use a linear log, or I could do what? If I'm looking for a nonlinear relationship, use a squared term of my x variable. Right? I still can use that other kind of quadratic model. But if I have these dummy variables, I'm going to be constrained to which of these 4 I can use. So categorical variables is another one we can't use, right? If I want to control for, what year you were in the school, freshman, junior, senior, it's going to be a problem. They're dummy variables, right? I can't do that. Not only that, let's say I had something like income. Well, yeah, I could do income. I can use, let's say I want to know the impact of income on life expectancy. If I use log models, what values can I not use when someone has an income of? So I can run that regression and it will tell me the relationship between income and life expectancy, but all the observations that are 0 are going to get dropped, which might be okay because maybe I don't want to use people who have 0 income in that regression. But anytime I have a variable that could have the value of 0, it's just going to drop those observations. So I can still run that regression. I'm just going to lose, and maybe those observations that are 0, that's important, right? That shows maybe that they're unemployed, and so maybe I still want those people in my regression if I'm trying to predict life expectancy. The other thing I want to make here, I'll get you guys out a little bit early here today. I don't know what's like your guys' highest level of microeconomics you've taken. You all have taken intermediate at this point, most of you. So if I take so let's say I had some data on price quantity. What's the interpretation of beta 1 here? So it's a 1% change in quantity. Actually, sorry, this isn't what I want. Let's do I'm writing this backwards. We could get there using that method, but let's do it this way. So let's say I have kind of a demand equation. How would I interpret beta 1 here? It's a 1% change in price causes my predicted quantity to change by beta 1%. What does that sound similar to? Yep. It's exactly what that sounds similar to, right? And in fact, if you have price quantity data, you can estimate price elasticities by running a log regression. Okay? So I'll try to go out. I've got some laying around. I've got some price quantity data sets. You can essentially take those price quantity combinations, come up with elasticities. How could I come up with cross price elasticities? Just include the price of other goods. 1% change in the price of the other good will change the percent of the quantity demand in this good by beta 2%. What about income elasticities? Natural log of income. So all these values that you've seen in other econ courses for elasticities, where do they come from? Log regressions. Now I know they show you how to do it like using the midpoint method a lot of the time in your basic courses, and then they kind of progress, but really that's where that's coming from, right? Is some type of a regression. And the reason why this becomes even more important, what can we do in these? Add in additional controls, right? So now I can really get a good idea about what this elasticity is, controlling for all these other factors as well. Okay? So before you guys get out of here today, I had a quiz, but we touched on logarithmic stuff, but I don't know, some of the questions I asked might not be fair in terms of how much time we actually had to cover them. I want to kind of save those maybe for an in-class quiz once we get back. So for today's in-class quiz, simply going to be showing up here. So I'm going to actually watch this to make sure you're all writing down one name because there's so many people gone, right? But on your way out, kind of write your name down. I'll kind of use those as kind of credit for being in the in-class quiz here today. We'll pick up on this nonlinear stuff once we return from spring break. Other than that, a fun, safe spring break. I'll get those solutions to the exam posted. So if you want to review that, you should have those this afternoon. Otherwise, I'll see you guys not next Tuesday, but the following Tuesday. Okay? So please make sure you sign in on the way out to get those points for being here today.